so we can get to all presentation. So the first presentation is a diachronic predictor of affective ratings of English words by Vladimir Teams. If any of authors are present here, please share your screen and go ahead with your presentation. Good luck.
So this is my presentation. Everybody see my presentation?
Yes, yes, we can see that.
Okay, right. So about diachronic predictors of effective ratings of English words. So words are the smallest meaningful units of language. Word semantic constantly changes, reflecting changes in our view of the word. So there are databases including semantic word properties used for psychological studies. One of the best is the MRC database. MRC database includes various word semantic properties, but MRC doesn't include some important dimensions of word meanings. These dimensions are, for example, valence, arousal, and dominance. We named them as VAD properties. These parameters are useful for studies in different scientific areas, such as social science, natural language processing, and others. So special VAD lexicons and dictionaries containing VAD ratings have been created. Usually such dictionaries are compiled by interviewing native speakers who rate these words. Our study objective of this work is to create a tool for obtaining diachronic estimates of VAD ratings. So it's about study objectives, about our data. We use NRC VAD dictionary with effective rating with the VAD ratings. This lexicon includes valence estimates, arousal, and dominance. So we normalized these ratings to the range from -1 to 1. And this plot shows that usually most of words have some neutral ratings with very negative values and very positive values. There are not so many. So also we used Google Books and Gram corpus. This corpus contains data of 8 different languages, but we use only English corpus. This corpus contains more than 2,000 billion words, and we used only diapason of time from 1880 to 2019. So we use only words from n-grams from this time period. So about vector representation of data. We used widely used methods of vector representation of words, and there are two possibilities. We use two possibilities for this. First one is using so-called fast text vectors. These vectors has only about 300 dimensions for each word. And we use also explicit word vectors, which used about 20,000 components for each vector. For example, we have some word, so-called target word, and we have many bigger grams. These are frequencies for this word with other words. And using these frequencies, we construct vectors. For example, this word disconnect. Disconnect is target word, and we have many context words like they, of, and, who, in, and so on. So totally 20,000 words. And for such co-occurrence, disconnect they, disconnect of, disconnect and so on, we have frequencies in the Google Ngram corpus. How many times this co-occurrence exist in the corpus. So these numbers we collect and prepare vectors for WX type and XW. So totally 40,000 components for each vectors. So then we use these vectors as input parameters for neural network. We use simple neural network with 4 hidden layers, size of 512 neurons, and one output neuron with valence, arousal, or dominance rating. So input parameters are 4,000 dimension vectors or fast text vectors, which are only 300 dimension. So we estimate we used different optimizers, we used different learning rates, we use also, we found that L2 regularization is the best for this task. We found that loss function is the best one is MSE. And then we trained our model. So about some results. Before results, about the data results, we divided our vectors to 6 groups with the same size, and then we 4 of 6 word groups were used to train the model, and 2 different groups for tests. So totally we have 15 combinations, and this is good for statistics and for more reliable training. So about comparisons of fast text vectors and explicit word vectors, CFW. We trained our model, and we used 2 types of vectors for analysis. We calculated the Pearson and Spearman correlations between effective rating values and their average estimates obtained from the model. We see the table with the results for 3 rating types and 2 types of vectors. Fast text vectors are very short, 300 components, and CFW vectors, they have 40,000 components. We see that fast text is a little bit better, but we cannot apply fast text representation of word vectors for diachronic studies. So we use only explicit word vectors, large vectors with a lot of components for diachronic studies, because we can prepare explicit word vectors for any time period using Google data. So this is comparing with machine estimates and human estimates of ratings, valence, arousal, and dominance. We see there's linear dependence, so it means our model is quite reliable. And about results, other results for diachronic studies, we use only explicit word vectors. We have large period from 1880 to present time. We divided this large period for small periods, and we use small periods for estimate VAD ratings. So the model was trained using all data, but we use only short periods for estimations VAD ratings using this data as tests. So 3 curves. This is dependence of Spearman correlation coefficient from years. We see that the correlation increase with years, and probably this is due to two factors. First of them, 100 years ago, many words have had a little bit different meanings. So the valence, arousal, and dominance estimates, which was done a few years ago, a little bit different if they would estimate it 100 years ago. It's the first one, and second point is second reason for such behavior of graph is 100 and more years ago there were not so many texts as in the present. 2 years ago, not so many books existed and newspapers and other text information as 5 years ago or 10 years ago. So second correlation, this is the dependence of correlation coefficients for depending on the corpus size. Does text a lot? How many texts in some? How many texts influence on the correlation coefficients? But this phenomena here near the 10 in the 10 billion size. This is due to Second World War, when the amount of books decreased during 1 year, for example, from 1939 to 1940. This time period, in this time period, amount of text decreased suddenly. So is this influence to the behavior of graphs, of our curves? So this is correlation coefficient depending on the time window size. We see that if time window size is large, in this case the correlation coefficient is a little bit bigger, because a lot of years ago not so many texts there were, and wide window consists of more information, more text, more words than narrow windows. And this is standard deviation of VAD ratings. And also we see the increasing with years. Where main hypothesis was the influence of the amount of text for the period. So we use correlated coefficient for this hypothesis. This is correlation coefficient. So it means that, for example, 100 years ago, amount of text was in about 30% less than today. So if we normalized our standard deviation to this correlation factor, so in this case we have not so many changes in the standard deviations. So looks like almost constant. So study case for this changes in some words during the time period. For example, word gain. We observe this decreasing starting from about 1960s, probably due to changes in the where is the meaning of this word. And so before 1970, usually this word had a little bit different meaning, some completely different meaning than now. So the emotion rating valence was different. So this word was more positive than today. But anyway, starting from 1995, about positive meaning was increased, and this tendency exists up to now. So if we see word bush, we see two peaks in arousal and dominance ratings, probably because of just there are two meanings of bush word. One of them is just common word bush. The second one is American president, two American presidents, George Bushes, and there are two, and two periods of there when there was in the political arena. And this is just confirmation of our hypothesis, just these are capitalization percent using of the word bush with capital B or small b. So there are two peaks in the percentage of using of the uppercase word bush. So these peaks are the same time periods. And last,
Vladimir, I just wanted to inform you that your time is up. You have one more minute to wrap up your presentation.
Okay, this is last example, and this is our conclusion. We performed estimation of VAD ratings using two variants of vector representation of words. For the predictors that used retrained fast text vectors, Pearson's correlation coefficient between human and machine ratings were 0.865, 0.792, and 0.799 for valence, arousal, and dominance respectively. Also, we estimated the Spearman coefficients for fast text and human estimates. Also, we have some values, and the examples described in the article show that affective ratings can be served as markers of lexical semantic changes. And diachronic one-line dictionary for English dictionary with affective ratings will soon be published in the Kazan University website. So that's all.
Thank you, Vladimir, for your presentation. And if anyone has any question, please, you can unmute yourself and ask your question from Vladimir. Not any question. So actually, I just have a very few questions. First, you mentioned that you use fast text embedding as a part of your experiments. My question is just some curiosity. Why only fast text? Why you didn't do any experiment using glove embedding or any other embeddings? Any reason behind choosing fast text embedding?
Thus, we have a dictionary with fast text representation, and we prepared our own representation of words, explicit word vectors. Just we found fast text and we use it.
Okay.
It was very surprised because only 300 dimensions results is a little bit better than 40,000 dimensions.
Okay. And in slide 16, can you show us slide 16?
Okay. 16. Okay. I don't see numbers. This one, right?
Yeah, this one. In the yeah, this one. In the figure in the right side, just I wanted to ask, what do you mean by corpus size? Is it the number of texts or number of books, or what it indicates?
Number of texts.
Okay. So I have no any other question. If anyone else has any question, again. So thank you, Vladimir, again. Please,
Yes.
you can stop sharing. And the next presentation, as I see in the timetable, is the interpretability of the BERT model in the context of semantic similarity from Diana group. Or if anyone from that group of authors exists, please share your screen and go ahead with your presentation.
Yes, thank you.
Vladimir, please, can you unshare your screen?
Yes, I cannot share my presentation. Thank you.
Thank you.
Can you see my presentation?
Yes, we do see your presentation, but your voice is not very clear if you kind of figure it out.
My voice is not clear?
No, it's not actually very clear. We can understand, but if you could improve it a bit.
Give me a moment.
Yeah, sure.
Can you hear me better?
No, yes, now it's better. Please start. Thank you.
Yes, okay. Well, I started. Well, my name is Diana, and I'm talking about interpretability of the verb model in the context of semantic similarity. Well, the problem is the transformer model like BERT are considered black boxes due its complexity. Also, BERT is relevant in natural language processing task. However, the interpretability has some advantage. With interpretability, you can identify some improvements of the model and also gives you clarity. In this project investigation, I realized that there are a lot of scientific disagreement in linguistic interpretability. The most of these works focus in the probes in the supervised learning method. So we address in the interpretability in the context of semantic similarity in the CCAIS token and attentions of the model. Based on this, we can set an hypothesis. We need to demonstrate the CCAIS token achieves better abstraction compared to other methods, and better attention abstract linguistic aspects, and the unsupervised learning provides reliable linguistic interpretability analysis. So BER means bidirectional encoded representation from transformer. It consists of a series of encoder blocks, and in each encoder there are attention layer and feed-forward layer. In the figure, you can see fine-tuning of the verb model for semantic similarity. You ingress two pair of sentence, and at the beginning of the sequence, there are CL token. This token is very useful in classification and regression like this to calculate semantic similarity. The objective of this token is abstract the global context in all the sequence. This is a state of the art for interpretability of bare embeddings. You can see, for example, in the reference number 3, the author mentioned that the lower layers as abstract surface aspects of language, like sentence length, and also intermediate layers abstract syntax and upper layer semantics. But then the reference number 4 mentioned that lower layers abstract syntax and upper layers abstract semantics. And the 5 reference, the new works, he said the lower layers abstract surface and intermediate layers. Sorry, I listened a voice. I continue?
Yes, please continue.
Okay. In intermediate layers, abstract semantic and syntax. This is my method. The bare analysis is divided into 2 parts. On the left, you can see the analysis for the CCAIS token. From the bare output, you can get the CCAIS token. This representation is the input for a regressor. That is my fine-tuning. And this, you can see my proposal methods, max pooling, min pooling, and bidirectional LSTM network. So the abstractions of these methods are the input in my regressor, and then I evaluate the semantic similarity. On the right, you can see the attention analysis. For this analysis, it was necessary I did a dimensional reduction to 2 dimensions with an autoencoder. And then I did a clustering analysis and evaluation of that clusters. And I interpreted the results in 3 aspects: sequence length, and semantic similarity, that is my label, and the grammatical structure similarity. And all these experiments, I use the dataset STS benchmark and SIG. This is the results of semantic similarity. You can see the CCAIS token was superior in Pearson and Spearman correlation to respect to my proposal methods. But what happened here? Well, in aggregation methods, in the case of min pooling, we are consider the relationship have equal relevance, but that is correct because in the sequence you have stop works. And in the case max pooling, you are considered that you only have the most important relation, and you have a loss of context for the information. In the case of CCAIS token, achieves a good abstraction that is difficult to overcome by the recurrent network, especially for round sequence lengths. Now, the results for in attention interpretability. Here you can see the cluster for all the layers. You can see the first 6 layers. There are a lot of dispersion in the data, and the last 6 layers, you can appreciate a better quality in the clusters. These are box plots. With box plot, you can analyze measures of central tendency, for example, median. In the case sequence length, for example, in the layer 3, you can see 3 clusters. 3 clusters have different interquantile range. So that means that the 3 clusters are different. One cluster groups low sequence length, other middle sequence length, and the third cluster groups high sequence length. So you have 3 different clusters. In the case semantic similarity, for example, in the layer 9, you can appreciate 2 clusters. So you have a cluster with a low semantic similarity, a small semantic similarity, and the other is high semantic similarity. And the same with the grammatic structure similarity, for example, in the layer 11 or 12, is the same. You can do cluster difference. I implemented a visual tool to understand the behavior of the data. For example, in the layer 1 for sequence length, you can see how the model tend to order the samples according to sequence length. But in the layer 8, you can appreciate the lower middle sequence length.
Claro, que eso es lo que dijeron que ellos terminaron haciendo. Están simplificando la imagen para que puedas tener el resto de
Excuse me, Annabelle, I don't know who is Annabelle. If you can mute yourself, yes. Please continue, Diana.
So in the layer number 8 in sequence length, can you listen me?
Yes, we can hear you. Please continue.
Thank you. In the layer 8, the low and middle sequence length starts to combine. In the case semantic similarity in low layers, for example, layer 2, you can see dispersion. But in layer 10, you can appreciate a separation of similarity 0 and similarity 5. In the case grammatic structure similarity, in all the layers, the samples tend to keep together all the samples, but there are more dispersion in some layers than others. Here you can see a statistical test using Kruskal-Wallis and Mangbin-Yu. You need to calculate a p-value. A p-value is a probability. If the probability is low, that means you have different groups, different clusters. So you can appreciate in the case semantic similarity for layer 6, 8, 9, and 10. The results are lower in p-value. Is the same case in the two datasets. So the result is consistent. In the case sentence length, the model focus in the first layers. And in the grammatic semantic test, only the layer 2 and 5 are similar, and the rest of the values are different. So my conclusions, the results are similar to the state of the art, but with the method supervised learning. Results in both datasets are consistent, but with difference in grammatical structural similarity. So the hypothesis is demonstrated to be correct, and the two-dimension attention abstraction provided understanding despite considerable reduction. That is all. I don't have have questions.
Thank you, Diana, for your presentation. Is there any question from other audience right now? Diana, I see a question in the chat box. Do you want me to read for you? From Sergio, he said thanks for your presentation, and he has a question: how you decided the amount of clusters to experiment with?
Yes, it's a good question. It was difficult to me. Let me give me a moment. Okay. Here, well, in the block in evaluation on the right, you can see some metrics like Stivet, Davis Bowling, Kalinsky Harabas. These metrics are extrinsic metrics, and these kind of metrics measure the quality of the cluster. So I plot these measures for different K cluster values, and I get with the optimal in each metric, like consensus decision consider the three metrics.
Is there any other question? You can write in the chat box, or you can just unmute yourself and ask your question in case anyone has any other question. Okay, meanwhile, I have a question. Can you move to slide 5?
Yes.
It's just probably something I want to check again.
5 here.
Yes. So here you mentioned the state of art models and the results. I believe the results, you mean the findings they have. And can you compare your finding with this finding? I hear that you said you found the kind of similar findings, but can you just a bit elaborate on it?
Sorry, but I don't understand the last part.
Yeah, I asked if you can just compare your results with the state of art results. As you mentioned, they have similar results. You obtain similar findings, but it's completely same. And the only difference is that you use unsupervised method.
No. Well, I think my results it's similar in the reference 5, for example. You can see that semantic similarity begins from layer 6 to layer 10, So I think it's similar to the reference number 5. And the number 3 and 5 is the same idea in the surface aspects. The surface aspects is like sentence length is the same. Is the same. The syntax in this case, in my case, was difficult. I think I consider I need to deeper in this part with other kind of methods.
Okay, thank you. Thank you for your presentation. If anyone has any question meanwhile, if not, we shall move to the next presentation. Diana, please, you can unshare your screen, and thank you again for your presentation.
Yeah, sure. Thank
So
you.
the next presentation is a multitask learning framework for leveraging subjectivity of annotators to identify misogyny. So I think Jason is going to present this paper for us. Can you share your screen, Jason?
Yes, sharing now. Is it visible?
Yes, we can see.
Okay. So the work I will present is about sex scenes, but specifically we are tackling the problem of identify misogyny on the context of subjectivity of different annotators that have different profiles. And for to this end, we proposed a new, can say, a framework for multitask learning. So this is, in summary, what we present. First, the problem we are solving. Why is this is important to be solved? The model that we develop, the results we obtain from our experimentations, and what we learn from this work. Also, what's next. So what we are working here specifically is about detecting the sentences in which there is a mistreat towards women. And this can be presented in different ways. Also in across time in natural language processing community, it have received different names. For example, it's hate speech sometimes, or offensive languages, or I don't know, any other different ways for discriminating women. And this is a big problem, and we are working with AI system to detect it. For example, for content moderation in social networks. But the problem here is that we rely on annotators, and it is very problematic because humans disagree about what one should consider to be misogynistic. So, for example, one can have different belief because of the background or the culture, or maybe they don't know very well the phenomenon and they misjudge what is a misogynistic practice or expression. Also, it could happen that related to the above situation above, it occurs that there could be different type of misogyny, or someone could be exposed mostly to specific types of misogyny and is then ignoring the rest. For example, are very subtle. In those cases, is kind of figure out what is a misogynistic content. So so one can say, okay, not anyone should be considered a good candidate to annotate misogynistic content. And specifically, what happens when someone ignores those kind of situations that we create models that are not effective to solve the problem. We can say that specifically there are two kinds of bad consequences that we want to avoid. For example, in the case of a system that is trained, for example, in some specific using some specific view or profile, it happened that those systems tend to be biased towards those specific perspectives that were considered during the training because of the annotator's perspective. So it is just mimicking or reflecting that annotator specific perspective, and that's bad because we know that it's very subjective. Um, and the other scenario is that it depends about what do you want to favor. It happens that you can create a system in which the user cannot trust. So it could happen that you may be too flexible and probably allowing misogynistic content to be present, and that's really bad depending on the criteria and the rules of the specific environment in which the system is working. Or it could also lead to the other extreme in which you are over moderating and then reducing, constraining the free speech. So that's also very bad. So how we think we can tackle this problem? First, we consider that we need a data set that includes different perspectives. So from that point of view, we can start experimenting with different models, and the best way to leverage those different perspectives to get some agreement. So this is part of another framework which is called learning with disagreements, in which you can have access to the different to several annotations from different annotators, but additionally you have also access to the background of those annotators, so like some metadata about the specific annotators. In this case, we have metadata about the gender and the age group. So we have here, like, for example, generational dimensions from this age, from 8 years old to 22 years old, and so on. From this dimension of female, in the case of female, we can then have a hard label. So what female thinks in considering the mode of the annotations across generation, and the same for male. And also, if we combine all of these, we can have a hard label. But it could have it happens that because we have here 6 different annotations or labels, it could happen that it's high, like in this case. In this case, the example is considered mostly misogynistic for females, but not that much for males. And in general, it's a tie. Then also happens that there are examples in which it's very, very conclusive. Like all male, or all annotators agree that something is um, misogynistic or not. In this case, for example, there are some, I would say, some variations in scenarios in which it's almost clear what is the label, but some people disagree also because of what I mentioned, that they have different backgrounds, different uh, maybe for example one can say that this specific male have exposition to some experience in his life that happened that consider this scenario to be misogynistic. Okay, so then how we tackle the problem, how we leverage this data. What we did is that we trained this multitask learning system. And in multitask learning, what we have are auxiliary tasks that are used to help a main task. So in this case, our main task was the hard level. And the hard level, I mean this hard level. So the way we leverage the data is that we construct different profiles. And we have here 2 subsystems. The first subsystem using 6 profiles. So we are using the 6 annotations from these the annotators as auxiliary tasks. And here we have a different combination, a different way to leverage the data. Here we use the mode or the hard label for males and females. So this is like from the using gender perspective, and here we are just merging all the 6 profiles. But at the end, what we want is to increase the performance for the hard level. So like getting the highest agreement on the task. For doing this, okay, yeah, we know we share weights, so the system is learning about the perspectives of each of those, depending on the aggregation we did, and then that, like I said, that tacit knowledge is transferred to the for the prediction on the main task. We did a similar experiment, but here all this architecture, the our multitask learning framework, was embedded in as a piece in a bigger system. In this case, we try the variation of what about if we freeze or update the parameters for those multitask learning encoder. So here we have the our initialization of the using some language model. But depending on the scenario where we are, for example, full fine tuning or freezing, we are not updating the parameters. So in a sense, this is here we have like a single step, because we are training everything on this auxiliary task and then predicting on the main task. But here we are leveraging the the profiles to train this multitask learning encoder. And then depending on the scenario, we update or freeze the parameters to then on the second step use a classifier for the higher level. Okay. Then these are the results we obtain. As you can see here, it turns out that our system that used two profiles was performing consistently better than the others. This is the one that is using single task learning, our baseline. Uh, and by the way, this is also the baseline because it's probably the first choice that someone would do when facing this scenario. When we have this, we just use this hard level as training and forget about all of this. So what we are demonstrating is that the power of leveraging the different perspectives. When we just don't ignore those specific labels for specific annotator profiles, then we can obtain a better performance from our systems. And that's possible because of the multitask learning framework. So these are the results for the first system I show you. I mean this one that is using like a one step for making the classification, and then this other one are presented. I present the result here. So here we have much more experiments. And as you can see, we try two different language models, Roberta and Twitter Roberta, just to see if there is some variation or some advantage of using Roberta, the Twitter domain. We made this additional experiment, by the way, because this data is coming from Twitter. So we wanted to see if a specific language model trained on that specific platform would perform better just because of that. What we can see here, considering the different initialization, is that the difference is not really significant across all the experiments we did. But we noticed that it's very significant considering the method we use. So in the case of full fine tuning using single task learning, as usual, we are having this 84, and then consistently we are getting higher results on all the other scenarios in which we are leveraging the different annotators perspective. Similarly, but much worse for the case of freeze in single task learning, uh, is very bad compared with updating the parameters. But it's not that bad when we are using multitask learning. So even if we are freezing here, the results are very competitive with updating the parameters. And this is good because then we can say that the machine trains faster, and we can get, let's say, less expensive results. Um, Then we made some error analysis in which we consider different categories just to see how the model is making mistakes. These mistakes you are seeing here, like the error type false positive or false negative, are mistakes that all our system made. So all these, I would say, yeah, all these six plus these three. So these nine models made the same mistakes on false positive and false negative. So we found these cases interesting because it's like the borderline of artificial intelligence, at least in our experiments, because no one of our system was able to pass those samples well. So we have here, for example, claim about misogyny. In this category, we consider that the test is about misogyny, but the system wrongly classify what is happening. Probably here because of the term miscarriage, which is related to abortion. Also mention some other words, like for example, opportunistic job. Yeah. So probably that's the reason why the system failed here. And here the system did not understand probably some complex scenarios like the term phallocentrism. Probably that's a reason why you cannot see that this message entails some misogynistic meaning. There are some complex references, some of them related to things that happen visually or in the real world, in the 3D world. For example, in this situation, it's describing in a scenario in which one can consider that a woman could be mistreated, and this probably is very hard to detect for a system that was only trained using textual data. And of course, there are scenarios in which there is not enough context. So maybe these cases could be or not be misogynistic depending on the specific content that is missing on the tweet. In this case, probably let's say that this is a comment, then the context is about the rest of the comment or on the post, but we are not considering that context. So it's understandable.
Jason,
Yeah.
Jason, I just wanted to say you are running out of time. Can
Ah,
you just wrap it up, please?
yeah. So
Thank you.
in summary, we learned that the diverse incorporating diverse perspective makes sense. It's very impactful, and that using multitask learning is effective for leveraging those diverse perspectives, and that choosing between Roberta Twitter and Roberta actually is not that relevant, at least not for our experiments. And we want to just expand our research on different scenarios, like exploring different languages, sources of information, and seeing how different cultural backgrounds could impact on the interpretation of misogynistic content. Yeah, that's all. Thank you.
Thank you for a very nice presentation and important topic that you have covered. So if anyone has a question, please, you can write in the chat box or you ask your question directly here. No, any question? So I had actually just a question regarding the data set. You didn't mention that what was the size of your data set and like how much training data and how much test data do you have in these experiments?
Yeah, I'm not presenting here. Those details are specified in the paper. And I can't remember, but here we have around, I think, 4,000 examples for training. So it was not that big, but I think that the ability to leverage different labels brings like some kind of documentation for our scenario.
And did you use the same training data and same test data when you were doing experiment with different like setup? Because I don't know if you were using like train test split only, or because those
Um,
results can be a bit
yeah,
changing.
those kind of situation or choices can be tricky sometimes, and where it's possible
Mm,
that one can make mistakes very easily. So
mm,
here, probably we are kind of covered because we are using the data from a shared task. So they
mm,
already make a lot of consideration for avoiding bias.
Yeah, thank you. And can you go to the result table?
Yes. This one or this one?
Yeah, this one. I just wanted to ask, these results are in average, right? And they are weighted, or if macro average?
Macro. All of them are
Okay.
macro.
Yeah, so they seem very promising. And how did you compare your result with the result in the shared task? Are they better, or how different are the results compared to the results they obtain in the literature?
Well, what we notice is that we wanted to compare specifically with people that were using similar approach for leveraging the profiles, but we didn't find like a direct comparison,
Mm-hmm.
because in those scenarios, specifically for shape tasks, they try to to use or introduce many mechanisms to improve the performance. So many of them also included documentation. Also, some of them made translations. Yeah, so it's like it's hard to compare, and we didn't consider that fair to compare in those scenarios. But in considering just about the scores, we would be on the second place. If that would be.
Mm-hmm. Yeah, yeah, nice, nice. Thank you. Any other question, please? I think there is no more question, and thank you again, Jason, for your nice
Yeah.
presentation.
Yeah. Thank you.
Yeah,
And great question. Thanks.
yeah, good luck. And okay, the next presentation is by Zara Ahani, which is utilizing deep learning models for identification of enhancer and super enhancer based on genomic and epigenomic feature. Can you share your screen, please? Can you hear us?
Yes, I can. Just a moment, please.
Yes, now we can see your slide. Please proceed.
Hi, I'm Zahra Hani. I would like to present my work on utilizing deep learning model for the identification of enhancer and super enhancer based on genomic and epigenomic feature. Next slide, we have table of content. We have introduction, related work, and methodology and result. What is artificial intelligence? Artificial intelligence has long been recognized as a dynamic domain within computer science research. One of the first methods in the field of artificial intelligence research was to use the concept of neural network and deep learning. In this slide, we have application of deep learning such as bioinformatics, pharmacology, medical, and industry. Things We can work in bioinformatics or regulation of gene expression and protein structure prediction, analysis of string, and segmentation of imaging. Also, we can work in medical drug diagnosis, imaging, diagnosis prediction, and biomedical engineering. Now I want to define some concept. One them of is enhancer from segment of DNA sequence that not only enhances the transcription of related genes but also play an important role in determining the expression of a particular cell type. Next concept is super enhancer. A set of a super enhancer is called a super enhancer. What is the epigenomic? The process that change the gene expression without changing the nucleotide sequence of a gene is called epigenomic. But deep learning represent the most recent advancement in the field of machine learning, emerging as a significant achievement and the central focus of research. Here we have we refer to deep learning method for is network and neural network and convolution network. That convolution network divided two sector, one-dimensional convolution and two-dimensional convolution. Both related work. In 2019, Han and Zhang used random force SVM-KNN and another method that I wrote here to analyze the super enhancer and similar data or else, to ours. But we have methodology. In this study, we consider 12 sets of features, DNA sequence, HMS, and chromatin from GEO. This data set include 5168 super enhancer and 5168 non-super enhancer. We consider for super enhancer a positive class, and we consider for non-super enhancer negative class. 45 features are considered for each case. This feature include 20 features related to chromatin, 11 for transcription, and 11 for motif, and 3 for trans specific information. Here we have a DPNN in hidden layer of a neural network method. A linear transformation on input data is initially followed by the application of a nonlinear function. This enables the network to learn a new feature space, which the output of these steps becoming the input for the next layer. This process iterates until reaching the fine layer output layer. Here is a convolution method, one of the most common deep learning in solving machine learning problem, which have been widely used in imaging and video processing or CNNs. What is CRAS? CRAS is deep learning library in Python that we use to build a neural network. In the last sector, we have result or convolution. We examine and compare the two prediction of super enhancer based on the two-stated method and using genomic feature. Both methods were model and analysis based on CRAS in Python. We did show results based on DPNN method. The cross validation method VK = 10 was used in this purpose. Here you can see a table that is about prediction result by DPNN method and using genomic feature. About next table is about prediction result by DPNN method and using epigenomic feature. So we obtained average for each criteria. Next slide, there are prediction results by DPNN method and using all the features. In this, we have the following chart is based on the average evaluation criteria in all categories of the cross-validation method with the DPNN method. You can see there we showed epigenomic with green color and genomic feature with red color and all feature that we used I showed with blue color. All analysis steps of DPNN method were also performed for convolution method. Again, we did and consider the k equal 10. So here there is prediction result by convolution 1D method and using genomic feature. Next table is about same method with epigenomic that here is the prediction result by convolution 1D method and using all the features. In the figure is based on the average evaluation criteria on all categories of the cross-validation method with the convolution 1D method. You can see the result that we obtained is the best result with convolution method, convolution 1D method on epigenomic feature. And the last, we have conversion of DPNN method with convolution 1D. And finally, ability to methods, DPNN and convolution to predict super enhancers is investigated. For this purpose, we again analyze the average value of evaluation criteria on all categories on the cross-validation method for all three groups, total, genomic, and epigenomic. Here we have the two diagram. In the right side, you can see comparison of prediction result for 2 dependent method and convolution 1D using in genomic feature group. But next diagram is about comparison between two methods, dependent and convolution 1D with using the epigenomic feature. But we have comparison of prediction result for two methods, dependent and convolution 1D, using the total feature group. And according to obtained result, the convolution 1D method has obtained better result that the result of Han and Zhang paper is the group of epigenomic feature. Here we have all result of research and we have Han and Zhang research result. You can see precision in all research is 0.95 and precision in Han and Zhang research is 0.89%. Also, F1 score in our research is 0.94 and F1 score in Han and Zhang research result is 0.85. Thank you for your attention.
Thank you, Zahra, for your presentation. It seems a nice work and you have improvement in the results. But first, let's see if anyone has any question regarding this. presentation. If you have any question, you can write in the chat box or you can just unmute yourself. Meanwhile, if no one has a question, actually, can you move to the slide where you were presenting your comparison of results using DNN or convolutional method?
Yes.
Yes, here. Here, as you mentioned, you are going to compare the results between genomic and epigenomic. But what I see in the figure is genetics and epigenetics. Are they the same or is there any difference between them?
Yes, genomic refer to a study of an organism complex set of genes. This concept is some concept about bioinformatics in genomics and biology.
Yes, I agree. But if you check in the figure, you mentioned genetics, not genomic, and epigenetics. Are they same?
Yes, yes. Excuse me, your voice is poor. Yes, it's genomic and genetic.
Okay, actually, it's not my domain of expertise. So if anyone else has any question, please feel free to ask your question, or we can move to the next presentation. I don't see any question chat box as well. So thank you, Zahra, again. So please stop sharing your screen and we may.
Thank you, thank you.
Move to the next presentation, which is by Antonio and his co-authors, which is entitled with Assistive Technologies for American Sign Language. Can you unshare your screen, Zahra, so Antonio can proceed with his presentation?
Hi. Hello. I'm Yel. I'm co-author, so I'm going to be presenting my screen. I'm going to present my presentation.
Yes, please. Thank you.
Okay. Okay. So let me share my screen. Okay. Can you see my screen?
Yes, we can see your screen.
Okay. All right. Okay. Can you see it in full screen?
Yes, we can see. Thank you.
Okay. Perfect. Okay, well, so hi, we're going to present this paper, Assistive Technologies for American Sign Language Users. This one is a state-of-the-art systematic review. So now let's start presenting some of the bases we have here. So first, the American Sign Language. Well, basically, it's a visual gestural language primarily used for deaf and hard of hearing community in the United States and some parts of Canada. And of course, something that we don't include here is that it's actually almost the standard for sign languages, and it's really spread out in the world. So yeah, that's why we focused exactly on this sign language. Now, what is an assistive technology? Well, this one is for people with some disabilities, encompass a broad spectrum of different solutions, focusing on accessibility and enhancing the quality of life for these people. And this technology includes devices, software applications, mostly software applications, and wearable devices that assist individuals with visual, auditory, motor, cognitive, or any other disabilities they have. As you can see, here we have some examples. For example, the first one is for some motor disabilities. The second one is for language disabilities. And the third one is interpreter, actually, that we're going to talk about them later in this presentation. And now we have the assistive technologies specifically for American Sign Language. Well, in this case, we are talking about individuals with deafness or speech difficulties and we can offer any innovative solutions to enhance communication and inclusion. We're going to talk about this more on the discussions and on the results we obtained, but it's pretty interesting about how to talk about the bridge of the gap of the communication between ASL users and those who are not familiar really with that language. So yeah, that special focus is pretty interesting for this research specifically. Now we'll talk about the research method we employed. So, well, basically we employed the systematic review approach. The reason is because we wanted to have really context, a broad context about what research is made towards this topic. And the goal is to provide a robust and unbiased summary of the available evidence, available papers, and available research. So here we can see our steps. First, we identify a search engine. Then we define a search string. Then we conduct an automated search. We we screen the search result and then identify relevant papers. So how we did this, basically we used the renowned Scopus database because of its really large database. Then we identified a search string. As you can see in the first picture at the right, that's our search string. We included the AI assistant, personal assistant. We also included any other assistive technologies specifically. Also, we used American Sign Language as one of our tokens, and of course, human-computer interaction because of the focus on this paper about the human-computer interaction, accessibility features, and any other kind of research or UX methodology used on these papers. We also define a search string. We conduct the automatic search using the criteria described on the right image, in the second right image. And also we read all the resulting papers from the search. And as you can see, we identified the most relevant papers and classified them. In the table 3 image, you can see when we did our search date and also how many documents we had as a result. We had 91 papers as a result and only 48 relevant papers. Of course, we then read in depth all the 48 papers to finish the classification. And then, well, we define our research questions. The first one is the distribution of the contributions, we're meaning the papers, of assistive technologies for American Sign Language categorized by country. The second one is categorized by year. The third one is categorized by impairment type. The fourth is categorized by the assistive technology used. And the fifth is categorized whether if it has an HCI perspective or UX methodology. What is interesting about this paper among any other systematic reviews or mapping studies that we research they have assisted is about these 5 questions, these 5 research questions, because normally these kind of papers only had 2 or 3 research questions, and they don't have the impairment type categorized, for example, and also no other had the HCI perspective categorization or any UX UI a perspective or any human-centered design, basically. So what is relevant about this paper is not only joining all these questions, but also improving that context we can have about the impairment type and whether if it's using human-centered design perspective. But well, we can now talk about our results. The first 3 questions are basically more quantitative questions, more about having the context, then we can have some discussions. But the last 2 ones have really in-depth research on our paper. So for example, talking about the first research question. As you can see here, we have chlorophyll math. And then, well, what we did is to identify the number of published relevant papers across the world, across every country. So we categorize the papers according to the author's affiliation, where the paper was published. And of course, if the papers were written by 2 or more authors of different countries, well, these papers were duplicated and counted for each country, basically. We're not going to talk about the discussions later. So now we can see this graph for the year. So basically, is to identify the quantity of articles published per year. This one is pretty interesting because we can see a really high trend on 2020 and 2022, between 2020 and 2022. And it's pretty interesting because if you notice that is during the pandemic. So yeah, we can conclude some kind of stuff from here, sorry. We're going to discuss this later. For the third research question, we have the categorized by impairment type. This one is a new we implemented on our research paper. So basically, it's not the same context to have if the research is oriented to speech impairment, for hearing impairment, or for both, because it implies different solutions or different assistive technologies applied to the research or proposed as a solution. So basically, we use the classification of disabilities by the Indiana University here, to have a base on how to classify or categorize the papers. And here we can see our results. Then this is the first one that is really in-depth study about what we did in here. So basically, this is the categorized by assistive technology used. We actually used the National Institute of Deafness and Other Communication Disorders classification of assistive technology. So well, basically, we were categorizing them by captioning, personal assistant, theoretical application. That means that it's not a direct application, but they propose some solutions for any issue, and interpreters and translators. So here we can have a really important trend to interpreters and translator, but let's talk about the similarities and differences of all these papers. So for example, as similarities, we can appreciate a classification of interpreters, translators, captioning, and personal assistant, the use of video and motion recognition to register the ASL language. So basically, how can we make a caption, and how can we connect to a personal assistant, or how can we create an interpreter or a translator by video motion recognition of the movement of the hands. And also, of course, if we can, have a text and then put it into an interpreter or pass this information by an interpreter, we also need natural language recognition to make this possible, to make the interpreter to actually interpret the text that we provide. So here we can see a real trend on AI solutions. And as well, the use of centered neural networks to translate these images into text, of course, for personal assistance, among any other similarities that you can see in depth on our paper. And now, talking about the differences, some is about the perspective of the translator. As you can see, we can have text to video and video basically to text, or video to text and then to connect to any other technology. So, well, basically here we have that text to an avatar, that they are the interpreters, and others to connect the language to recognize other technologies as video conferencing tools and personal assistants. The video conferencing tools solution is pretty interesting because basically they are based on captioning. So for example, if we are like this on a Zoom and I'm talking on ASL language, using these neural networks to translate my videos, my video, my hands movement into actual words, into actual phrases. And of course, personal assistance, because we need this translate to text and then to paragraphs and then put it into a personal assistant. So it's pretty interesting, the similarities and differences. It's pretty interesting, the characteristics of each one of the assistive technologies and the solutions they provide. So yeah, that's why we included this specific research question. Now talking about the fifth one, the one that I think that makes our focus really different among any other paper, is the if it has an HCI perspective. Well, we use the NNG Nielsen Norman Group classification of types of impairment and types of HCI methodologies. So here we have the remote usability study, not includes our usability study, the in-person usability study, field study, of course, the benchmark testing, that is it's pretty common in these kind of papers. Well, basically the main similarities that propose is that where if they use an HCI research method, they prepare a demo of the service, of the product, of the solution. So basically, if we know they have an HCI perspective or HCI research method, we know they prepare some kind of demo, some kind of questionnaire for the users. And that's pretty interesting because we can have with these papers more context about whether if the solution worked really or it didn't. And also, the main difference is that while the papers did not support a method, they only tested theoretical solutions. So basically, if we don't have a method, a research method, we only have theoretical solutions, as you can see in our last research question. And then, well, let's talk about the discussion, what we really get from all of this research. So in the first research question, we can see a trend on the COVID-19 pandemic that you can see in the years. Then we have the second, that is a type of disability. And this is evident that, for example, hearing impairment, speech disability, and the combination are receiving most attention among any other. So this specialization that, as we can see in our research question, indicates the recognition of unique challenges and requirements in all of each disability. So basically, the research are only or primarily focusing on one of the disabilities. So basically, that's what we can get from here. Then about the proportion of research related to interpreters and translators on RQ3 that we can see in here. So, for example, we have 44.6% of focusing on interpreter and translator, and this is pretty interesting. We're going to discuss it a little bit later in a moment. And then the theoretical application are representing 37.5% of the articles. So what we can see here really is that the adaptation of technologies such as personal assistance, video conferencing tools, and sublink tools for this specific group received relatively less attention than actually translating them or helping us to communicate to these people. So basically, what we see here is a trend about bridging the gap between communication and not really bringing these technologies or these modern technologies to them. So that's pretty interesting. That's something we can conclude to make further research. And then, I'm sorry, I think we repeated the RQ4. I'm so sorry, it's the same as the RQ3, but let's talk about the RQ5. That is the UX research method. And we can see that 57.14% utilize actually our research question. And this is pretty interesting because right now we can see that we have a trend to actually using HCI methodologies to validate the usability of these solutions. And I think it's pretty important because the real heart of all of these disability solutions, of all of these assistive technologies, is really the usability and the accessibility they bring to these individuals. So, well, we can see that we have a positive trend in here, but also we have never had this perspective in any other systematic mapping review or literature review. So it's a pretty good thing to get from this research. Talking about the conclusions, well, while the research area of assistive technologies for ASL has gained significant relevance worldwide, many articles propose innovative technologies, yes, but the main focus is on improving communication for ASL users, particularly through development of enhancement interpreters and translators. And this is relatively less emphasis on adapting conventional technologies for this specific user group. We're talking about personal assistant. We're talking about the new AI technologies we have like ChatGPT. We are talking about, for example, video conferencing that right now is a tool that is really important. We're talking about technologies that we normally use in our daily life and is not getting into them. They are not using them basically because they are not prepared to be used by them. Well, based on these findings, it can be concluded that there is room to improve the accessibility of these technologies, of these modern technologies for users in different contexts with different disabilities, specifically for speech and deaf disabilities right now in here. And last but not least, well, I wanted to share this quote from Deborah, that accessibility allows us to unlock the potential of everyone. So I do believe that this paper and all of this further research we can have from here is really important because we can improve this accessibility and make everyone to contribute their way they want to everything they have their role put on. So yeah, that's so far.
Yes, thank you, Miguel, for a nice presentation and a very well organized presentation. So if anyone has a question, please unmute yourself or write in the chat box. So it seems there is no any question. Thank you, and again, congratulations on your nice work. So we may move to the last presentation, which is communicative intention detection in Spanish tweets. If the authors are here, please share your screen.
Hi, everyone. Can you hear me?
Yes, we can hear you.
Great. So, are you hearing my screen?
No, we cannot see your screen yet.
No, can you see my screen?
Yes, no, we can see your screen. Please start your presentation. Thank you.
Okay, well, good afternoon, everyone, and thank you for attending this presentation. My name is Alex Valencia, and today I have the pleasure of presenting my research work titled Communicative Intention Detection in Spanish Tweets using Jacobson language functions. Well, in this study, we have focused on exploring how the language functions proposed by Roman Jacobson can be applied to identify communicative intentions. This analysis is based on the previous contributions of Richard Arcand and Nicole Bourdieu in this field. My motivation is not only academic, but also practical, as a better understanding of communicative intentions in tweets can have significant applications in areas such as marketing, politics, and crisis management, among others. Well, first of all, what is communicative intention? The communicative intention is the purpose that a participant in a communicative act aims to achieve truth discourse. The intention shapes the sender discourse, as their linguistic acts will be directed towards achieving the intended purposes, even unconsciously, while influencing the receiver interpretation. Okay, based on this idea and considering Jacobson's language functions showed in this slide, which are as follows: referential function focused on the context or referent. Its intention is to inform. By another hand, emotive function focuses on the sender and their personal expression. Its intention is to express emotions. Then conative function oriented towards the receiver. Its intention is to influence. Fatigue function centers on the communication channel. Its intention to. Metalinguistic function refers to the code itself. Its intention is to clarify aspects of the code. Finally, poetic function focuses on the message itself. Its intention is to stylize the message rather than its content. Okay, the corpus we select for carrying out the labeling of intentions, considering the practical motivations, was RepLab 2013, which has the following features. Originally, was used to evaluate online reputation management systems. In second place, contains the next labels for tweet: polarity, with values positive, negative, and neutral. and reputation impact with labels low, middle, and high. As third point, crawling was performed from 1 June 2012 to 31 December 2012, using canonical names as queries for each entity. Entity includes automotive companies, banking companies, universities around the world, and music artists. At 4 point, we take a subset of the RepLab 2013 corpus with a total of 2,653 tweets, selecting a subset of Spanish tweets, including 4 domains: automotive, banking, and universities, and music. Well, having the theoretical framework to define intentions and having selected the target corpus, I will now present a general summary of our research methodology. Initially, in data labeling, we create guidelines by linguists for the identification of language functions. Then we do tests until obtaining 75 tweets where all labelers assign the same label. These 75 tweets we use as tweets of control to evaluate every annotator. After, in that dataset consolidation, apply annotation consensus of language functions in tweets. For this, we use the work of Andrew Rosenberg et al. Then mapping of Jacobson language functions of two intentions using the work of Richard Arcand mentioned above. Finally, in that step, the results of the annotation process was a Cohen-Kappa of 0.63, which is a substantial agreement between annotators. In the next step, preprocessing methods experiments in ML, we evaluate the efficacy of various text preprocessing methods. These include handling symbols, emoticons, usernames like links, hashtags, and stop words. These preprocessing steps is common in the natural language processing field. Then we make a statistical analysis to compare the impact of different preprocessing methods and logistic regression and SVM classifiers on the classification results. In the fourth step, for n-gram feature sets experiments and ML, experiment word, character, and pose tags, n-grams, and the combination of them using different ranges along with different thresholds for minimum word frequency and in the document. Moreover, a statistical analysis to compare the impact of different n-gram feature sets. It was observed that a minimum of document frequency of 0.10% yielded the best results. Finally, in deep learning pre-trained models experiments, the experiments using deep learning pre-trained models based on the Spanish language from transformers, BERT, and generative pre-trained transformer, named GPT. Finally, we compared deep learning algorithms with machine learning classifiers. Deep learning models, particularly BERT Spanish. To share with you some of the most important findings of the research, we have the following. First, regarding the experiments of preprocessing methods ML, in Table 5, a summary of the individual preprocessing step results is presented, highlighting the combinations that achieve the highest average of F1 score. We use this metric because in our objective was every category of intention had the best classification results. Well, we conduct a statistical analysis using all combinations and a paired sample t-test with a significance label of alpha in 0.05. The alternative hypothesis considered difference in means, which the reference being the method that did not incorporate any preprocessing steps. As we can observe in table, the results in bold represent the two preprocessing methods, symbols and emoticons, and symbols, emoticons, and usernames, which achieve the highest values compared to the reference for each algorithm, and their means are significantly different. On the other hand, the method's minutes, link, hashtag, and stop, and link, hashtag, and stop yielded the lowest values. Additionally, it is worth noting that preprocessing that only involve converting the text to lowercase result in the same average values as the reference. Well, secondly, with the aim of conducting a linguistic analysis of language functions combined with machine learning skills, we obtained the following word cloud with the top positive coefficients of logistic regression model, and the insights are the following. The first is the intention to influence can be conveyed through requests that include engrams such as in Spanish, favor, por favor, in English is please, I hope, we want, listen, and don't. Each engram is oriented towards the intention to influence, encourage an action, or elicit a reaction from the recipient in a specific context. In second place, the emotional intention is present in various forms, including positive expressions such as in Spanish, amo or love. Okay is cognado in English. Okay, good, perfect, and louder expressions like ha ha ha, as well as negative emotions such as sad, in Spanish, triste. The essence of emotional intention is to convey what the addressee feels at a given moment, and this is reflected in the engrams I, me, no me, and I. The later sequence expresses sympathy or concern for something mentioned. Additionally, we find engrams that include symbols such as, in Spanish, exclamación pregunta, in English, exclamation question. This sequence combines exclamation and question marks, suggesting surprise or astonishment in a question. Finally, when making a contrast between the classifiers of machine learning versus deep learning pre-trained models, in this subset plot, filtered the results from the intersection of the 4 classifiers to enhance visualization. At this intersection, which represents 51.9% of correctly classified intents. A total of 630, we observed that the categories with the highest number of correctly classified instances are intention to inform and emotional, followed by stylish and influence. It is worth noting that in the clarified intention, there was only one instance that was correctly classified by all classifiers. However, the engaged intention was not present in this intersection. The black bars on the left side of the graph represent the number of correct classifications for each model. This data revealed that BERT Spanish performed the best in terms of accuracy, followed by the logistic regression model, SVM, and BERT multilingual. Finally, when comparing the results by algorithm type, namely machine learning and deep learning, we notice that deep learning algorithms achieve a higher number of correct classifications in the stylish category, but individually and in the intersections highlighted in blue compared to machine learning algorithms highlighted in orange. Well, our conclusions are the following. In first place, the study introduced a unique approach by connecting language functions of Jacobson with the intention of interlocutor on tweets. In second place, their research achieved a substantial CAPA agreement score, demonstrating the validity and robustness of the corpus used for automatic classification models. This underscores the reliability of the data labeling process. By another hand, emoticons and symbols provide essential information for distinguishing between different types of intention in machine learning classifiers. This highlights the importance of considering these elements in text analysis and in particular in text pre-processing. The study observed that the combination of character engrams and word unigrams yielded the best performance. And by another hand, logistic regression and BERT Spanish models were particularly effective, with BERT showing higher F1 scores values. And we consider the next future work. Utilize polarity and priority tags from the RepLab 2013 corpus alongside the intent label for deeper insights in marketing strategies and customer relationship management. Then analyze tweets with positive polarity and emotional intent about products, considering user profiles like gender and age to enhance customer relationship management. At third point, focus on reputation management by identifying negative sentiments in tweets and their impact on the reputation dimensions mentioned. At fourth place, explore the detection of intentions in user prone to disseminating fake news, especially when their intention is to inform or influence, and assess its impact on reputation and risk management. Finally, develop subcategories based on the intentions identified in this study to enrich the analysis of intention in Twitter. Well, this is my presentation. Do you have any questions? And thanks.
Thank you, Alex, for your presentation. If anyone has a question, please unmute yourself or write in the chat box. So it seems there is no question from audience. I just had a few questions about the annotation procedure. How many annotators did you say you had?
How many annotators?
Yes.
Excuse me? Yes, it was 6 annotators, six linguist annotators.
And how the final label was decided based on majority voting or something?
Excuse me, I can't understand the question. Can you repeat, please?
I asked how the final label for each text was decided. You had 6 annotators, so it was how you decided which one is the final tag. It was majority voting or how?
Okay, we used a work by an author. Let me give me a minute for the reference. Is mentioned in. Okay, apply a notation consensus of language functions in tweets by Andrew Rosenberg et al.
Okay. Yeah, that's all from my side. If anyone else has any question. So thank you again, Alex, for your presentation. And it seems we are into the end of this session. Thank you, everyone, and sorry for the technical problems that we had in the beginning. And thank you for your time. Good luck with your publications.
Thanks, and goodbye.
Have a good day. Bye.